Okay, everybody, we're going to start in with the chain rule. So this is how we start off. We want to know how to take the derivative of something like y equals the square root of x squared plus 1. Okay, and the concept is that we know how to take the derivative of a square root function. Okay, y equals square root of u. And we know how to take the derivative of a function like the inside function x squared plus 1. And the question is, ideally, we'd imagine that somehow the derivative of the entire function, the square root of x squared plus 1, is a combination of the two. And indeed, that's correct. So the question is, how do we combine the results that we have? Okay. All right. Let's take a look. All right. So first, we're going to call the big function, kind of the entire function, capital F of x, and it's just going to help with some notation. Okay, so we look at the function we're interested in taking a derivative of as the composition of two functions. That's what the chain rule does, is deal with the composition of two functions, one function inside of the other. We have to assume a couple of things. We have to assume that the derivative of the inside function exists, okay, and we have to assume that the derivative of the outside function, if I put the inside function inside of it, also exists. Okay? So both things both have to be true. Then this is the chain rule. The derivative of the entire function is the derivative of the outside with the original inside plugged in times the derivative of the inside. Okay. Here's another way to write it. Okay. And this is how Leibniz would have written it, which I actually think is in some ways more intuitive. Assume that y is the function, okay, and y has an outside function, which is f, and an inside function, which is u, basically. Okay, so the outside function is y, the inside function is u. They're both differentiable, so that's the exact same assumption as we have in the Newton version. Then, or really, again, I suppose this should be not Leibniz. It's actually not Newton's notation, but that's okay. So they're both differentiable. Then the derivative of the entire function is the derivative of the original outside function, if we regard the inside as just a variable by itself, times the derivative of that function evaluated at x. Now notice that in a sense we can think of these two things as canceling. Now that's incorrect, okay? In that differentials don't cancel. They're not really fractions, but you can look at them and think of the chain rule as sort of some sense of cancellation happening there. Okay, so dy du times du dx is dy dx. The reasoning is sound, but it's not a cancellation. Okay, so let's find a derivative. So y equals the square root of x squared plus 1. That's what we were looking at. Again, we look at the outside function as the square root of u, and the inside function is x squared plus 1. So we have outside and inside. And if we can take the derivative of each of those, then we've set it up nicely. Okay, here's what it looks like. Using the Leibniz notation, just to help us out with this, we take the derivative of the square root function. Okay? So the square root function is 1/2 u times negative 1/2, to the negative 1/2, right? We change this to u to the 1/2, and then we take the derivative of u to the 1/2. That's this right here. Okay? But we have the chain rule says we must multiply by the derivative of whatever u is. Okay, now u is this, x squared plus 1. U is the inside function. The derivative of the inside function is 2x. Oh, I made a mistake there when I prepared these. 2x. All right. So, dy dx is 1/2 u, the original u, to the negative 1/2 power. That's the derivative of square root function with the original function still inside of it, times 2x. Again, there's a mistake there. Fix that. Okay, times 2x. So the derivative of the outside function with the original function still inside of it times the derivative of the inside function. All right, let's try another one. Cosine squared of x. Okay, so cosine squared of x, we talked about this in class today, is really shorthand for saying cosine all squared. We apply x first to cosine and then we square. Okay, that's why we put the square here rather than here. All right, here's how we're going to do it. The derivative, and again, we're using the prime notation here, is treat this function treat this function as the inside function. Cosine is the inside function. So if we want to use the u notation, cosine of x is u. The outside function is u squared. So basically, do we know how to take the derivative of something squared? We do. Do we know how to take the derivative of cosine? After this last homework assignment, we do. So here's what we do. We take the derivative of something squared. It's going to be 2 times something to that first power. So the way the chain rule works is we say, bring down the 2, just like a power rule here, leave the original thing inside, but then multiply the entire resulting derivative by the derivative of cosine of x. So we get the negative sine of x here by noticing that the derivative of this function is negative sine of x. The derivative of cosine is negative cosine of x, and that's it. Okay, we can leave it like this. I suppose we could simplify further if we so chose, but there's no real reason to. Okay, let's do a quick proof. The proof is somewhat easy and somewhat hard, but I at least want to verify to us that it works. Okay, this is the limit we're trying to find. We're trying to find the derivative of the entire function, okay, which is going to be, using the x going to a notation, version of the limit definition of the derivative, f of g of x minus f of g of a, all divided by x minus a. Okay, so here's how we do it. We use a little trickery here. We introduce a new term, basically. We say, okay, well, that's f of g of x minus f of g of a divided by g of x minus g of a times g of x minus g of a over x minus a. All we've done here is we've introduced this other term, which then could cancel out. Notice that. Okay, and that's what makes those two the same. This line and this line. Okay. Now, we've introduced something, but this quantity g of x minus g of a, now, we don't care about what happens when x equals a, so that's not a problem. It can equal 0 when that happens, but the problem is that the way we've set this up, we're assuming that the f prime exists and that g prime exists, okay? We don't have any guarantee at this point that this thing is non-zero, okay, away from a. Away from a. So there's a little bit of discrepancy as to whether or not it's legal for us to introduce this term, because if we do, then we are not allowed to have a denominator of 0 here, okay? So it's just something to think about. And so what I'm going to do is, if you look up this proof in the book or elsewhere, you're going to see some interesting things done to solve that problem. It's very doable, but you have to be kind of particular and create a piecewise function, and it's not terribly important. The idea is what counts here, and that we are able to introduce this second term. Okay, but let's assume that it's going to work out okay. Okay, and if it works out okay, that means that this limit is well defined, and this limit is also well defined. But this limit is simply the derivative with g of x inside, and this limit is the derivative of g of x. And again, there's a typo there. I apologize for that. Let's fix this. The derivative of g of x. Okay. So the chain rule says the derivative of the outside function with the original inside still inside of it times the derivative of the inside function. And that's it. That's the chain rule. Okay. So a couple things just to remember. There is an inside function and an outside function. Okay, and that's how I refer to them, inside versus outside. The total derivative, okay, this is the language I've been using, is the derivative of the outside function with the original inside still inside times the derivative of the inside function. That's it. This is how I think of it kind of in general. The derivative of the whole thing times the derivative of what's inside. You'll hear me say that a lot. The derivative of the whole thing times the derivative of what's inside. All right. So the next thing to do is just to practice. Okay. Leave this this one for you. Got 3 for you here. And just practice. So let me just set these up just so you have a sense here. We have an inside function of x squared minus 2x minus 5 and an outside function of x to the 6th. Okay. Here, gosh, quotient rule, right? unless we decide to rewrite it as negative 4x cubed plus x plus 1 to the negative 3. Now our inside is the negative 4x cubed plus x plus 1, and our outside is something to the negative third. Okay, I'll leave this one to you. I think you can figure out what the inside and the outside are. And I'll mention to you that sometimes the hardest part about these are choosing what is the inside function and what is the outside function. Okay, great. So thanks so much.